Thank you, Professor Kim, for such an interesting talk. I'm sure the audience has found it immensely helpful. And I can see that there are a lot of questions coming in. So without any further ado, let's get started with the Q&A session. And I would request Professor Kim to share insights or your comments on these questions. So for the first question, Professor Kim, is on magnetophoretic removal technique that you have described initially. And the participant is asking about how does the efficiency of magnetophoretic removal technique compare with other state-of-the-art methods such as adsorption and so on?
All right. First of all, I have to confess first, right? I'm biased. Because I'm working on magnetic separation, I will tell you, come on, magnetic separation is the best in the world, right? If you really look at it, like realistically speaking, whatever I show you just now is considered cheating, right? Because it's a lab scale, right? A very small ball, and I just show you 99.999%. But in reality, I guess there's quite a number of companies actually. In fact, there's some Japanese company actually also developed this magnetic separation of microalgae. And I believe the real life engineering, large-scale engineering application that you do depends on the design of your magnetic separator, right? There's so many different kinds of separator. And I guess I would say it's around 50 to 70%. To play safe, I would say it's at the bottom end of 50 something to 70%, which is quite good, if you ask me, right? Okay. And of course, if you're willing to invest a lot on high gradient magnetic separation, remember whatever I show you is all done in low gradient. If you're willing to fork out a lot of money and go for high gradient magnetic separation, go ahead and you will manage to get a very, very high separation efficiencies. But of course, I believe it's not economically viable for long term.
Yeah. So another follow-up question, Professor Kim, Professor Lim, that we have here is the magnetophoretic removal technique you described reversible, meaning that could the particles be regenerated?
Sorry, again, the particles can be?
Could the particles be regenerated, meaning that when we remove the magnetic field, could we get it back? Like, is it reversible?
Oh, okay. So the whole idea is, can we recycle the magnetic particles and use it for second round? If not, then the whole thing is trash, right? You just use magnetic particles, very expensive if you can't recycle it. Okay, we didn't work on the recycling of magnetic particles because eventually, as you can see it, our attention was deviated into the micro robot. But there's a lot of people who taking over from us. They develop all kinds of technique, right? One of them is actually after they collect the particle, the microalgae cell with particles, right? So what they do is actually they just dissolve these particles by using certain kind of solvent and things like that, and reform the particles again and reuse it again. And some of them, what they did is actually they just lyse the cell. What is lyse the cell? I mean, they just break the cell, and eventually the particles that attach to the cell debris, and they will just recycle using it. And of course, efficiency is reduced, but the observation shown by one group, if I remember correctly, is from New York University. They managed to do it like 5 cycles, no problem. So realistically, you can see it that there's a multiple way for you to recycle it. But of course, large scale implementation of it is yet to be challenged.
Yeah. All right. Thank you, Professor Lim. I think that is the answer. So the next question is where the audience member is asking about the role of pH in the motion of microbots in the presence and absence of magnetic field.
The role of EH, you mean electrohydrodynamics effect, is it?
Yes. So does pH have a role in the motion of microbots?
Oh, okay. pH has a role. All right. Yes, definitely. All right. And I guess there's when you culture the cell, right? When you culture the cell, it depends on in which day you want to start using it to construct your microbot. And in each culturing day, the pH, of course, is different. The most obvious influences of pH is the attachments of the particles onto the cell, right? Because if we are relying on certain kind of electrostatic interaction, and the electrostatic interaction and can be pH dependent because it depends on the isoelectric point of your particles. If you are used, fortunately, most of the polyelectrolyte, at least the polyelectrolyte that we use, is pH insensitive. That means they are quite strongly charged, strong charge. In such a way, it wouldn't influence its attachment too much. And so the implementation of attachment 1 is completely pH independent, I would say. Then, of course, how active the microbot is, because it depends on the culturing days and things like that. That also pH dependence.
Thank you, Professor Lim. The next question is about a specific observation of a difference of about 11% in the viscous drag. So the participant is asking, why is there a difference of about 11% in viscous drag? So can you please explain it in terms of velocity, gradient, surface area, and nature of the liquid?
Sure. All right. I'm sorry if I didn't make my point clear enough. That's why you're confused. All right. Whatever we try to do this, force balance analysis, actually we know the thrust force from our experiments. Then we just need to estimate what's the drag force experienced by this construct, right? So the drag force of this construct actually is actually geometry dependence, because everything unchanged besides the geometry have changed, right? We're using the same cell, in the same kind of microenvironments, so the liquid environment doesn't change, the cell doesn't change. The only thing is the geometry of the whole construct have changed, because one is pick up another particles. So once we have this, we realize this point, and it depends on the geometry of it, we could use a factor to estimate what is the geometry change that can be introduced into the drag force calculations. And from there, we compare before, without particles, then we observe the differences in terms of viscous drag, which experienced by this microbot is about 11% differences. But however, in our experiment, we observe a 50% reduction in terms of velocity. And then we know it cannot be this 11% that leading to 50% because they are linearly dependent to each other. So there have to be some other contributions.
Yeah. Thank you, Professor Lim. The next question is related to the cargo peaking video that you showed. And the audience member is asking about whether all the movement measurements are done under the same magnetic flux.
Sorry, let me see. Which cargo, let me see. I believe whatever the cargo picking, like for example, like this one, right? Cargo picking like this one is without having any magnetic field being turned on. Remember, this is before it actually pick up the cargo. So what I want to emphasize, remember just now when it comes to magnetic forces control, the Weaving works, there's two parts, right? Helical motions and translation. And we are studying the helical motion region in which there's no magnetic field. So we want to check how the presence of a cargo that can influence the motion or transport behavior of this microswimmer. And eventually, of course, they form a robotic later on.
The next question from a participant, Professor Lim, is whether this technology can be scaled up, and how do we design a new robot if the impurities are unknown?
Okay. This is, I guess this is a very good question. If you ask me, to be honest, I have no answer for it. Definitely those who work on this is very optimistic, right? Because we have been come for very far from the very beginning. And now there's so many kind of constructions, and we also learn a lot about its motion and what is the external factor that influence motion, right? So microscopically, I guess we have achieved a lot in terms of understanding. However, in order to make it as an engineering reality, that means we want to apply it for somehow. We can't count on one microbot to make the thing works. We need to count on a bunch of them work together in order to get things done, right? And that part, I guess, is missing. I believe the main direction on this research, right, later on from this point forward, is to bridge the macroscopic collective motion, collective transport behavior of all the swarm of this microbot, and relate it to the single microbot. So we could generalize whatever we learn from a single microbot and generalize it to the collective transport behavior of all of them, that leading to engineering application. So there's one few puzzle is still missing, and there's a lot of people actually try working very hard to fill out all the puzzle.
Thank you, Professor Lim. I'm sure that is very optimistic about the technology.
Yeah. I guess if I'm not optimistic, I won't keep doing it, right?
Sure. Absolutely. The next question from a participant, Professor Lim, is is it possible to direct the magnetic nanoparticle to be attached to a specific site on the surface of the microalgae? And if so, then the hindrance caused by the restricted motion of the flagella, can that be avoided?
Okay, all right. The question is a very complicated question. There's few layers of physics involved. Let's try to talk one by one. If we are talking about nanoparticles, right? One of the reason why we are not using nanoparticles, but we are using micron-sized particles, as almost everybody else, none of them using nano, all use micron-sized particles, because we could see the micron-sized particles using optical microscope. That means we could really track their motion. And more importantly, if we have one single microbit and we attach to one microbot, we could know exactly how much magnetic material have been successfully attached onto it. If we have a swarm of nanoparticles all go in and attach to it, there's no way we could estimate the total magnetic volume that have been attached onto particles. Then we can quantitatively calculate exactly the magnetophoretic force being imposed on one single microbot. All right. And the second layer of the question is, when you think about it, right? Just now, I believe I mentioned something about the posterior attachment is much more challenging to accomplish, for a simple reason. When the flagella is beating, because it's moving, so it's always moving in the direction in which the flagella is stroking, right? This stroking motion actually creating a flow field around it. And it's almost like a suction that suck all the fluid around it to go in. And that's the reason it is much easy for having the microbits to go to the anterior part. That means go to the central part of the flagella. And if you introduce a swarm of nanoparticles or go into just let them to be picked up by this microswimmer, what's going to happen is, in most likelihood, most of the nanoparticles are going to attach onto the anterior part and stick all over the flagella. And I suspect, I haven't done any experiment yet, but yeah, I'm just making an educated guess. The educated guess is this: most of the nanoparticles will actually attach onto the flagella and anterior part and suppress the motion of the flagella. So it might not be a very good strategy to do it.
All right. Thank you, Professor Lim. The next question is about swimming speed, where the participant is asking about how does the swimming speed affect the magnetophoretic removal efficiency?
Okay. I guess the questions, I think the audience who asked this question is too kind, right? The question is, you are talking about micrometer per second, right? So by the time we finish the whole talk, the particle, the whole 1 hour, 3,600 second, right? 3,600 times 10, 36,000 micrometer. 36,000 micrometer is 36 mm. It's nothing, right? In 1 hour, by the time I end the talk, they just move 36 millimeter, right? But remember, we are talking about motion of one microbot. Like what I explained just now, if we want any kind of this technology to work involving small material, nano material, micron-sized material, we count on a collection of them, a collective motion of them. And when it comes to collective motion of them, the magnetophoresis actually is a very beautiful phenomena. In fact, the magnetophoresis can actually go through a regime called cooperative magnetophoresis. That means the magnetophoresis of single particles actually influence each other, and they can move together, and they can move at a much rapid condition. That means can move at a much faster velocity. And that's the reason when you look at the separation of the microalgae, right? Even though in terms of individual particles, they move at very slow speed, but when it comes to the whole microalgae separation, you can observe just now, the time it takes in order to achieve the complete separation for lab scale experiments, roughly is about in 90 seconds. So it's a very rapid process, right? So yes, whatever the magnetophoretic velocity that I reported here is in micrometer per second. However, if you go to macroscopic scale with a lot of them move together, you are going to observe a much faster process.
Yeah. Thank you, Professor Kim. I think in the interest of time, we'll just pick up one last question where the audience member wants a bit more detail on the fabrication of the microboards. So if you can slightly elaborate on the fabrication of microboards, more on the functionalization and the preparation.
Okay, all right. Actually, there's no any secret recipe. You know, everything is very straightforward, right? Of course, if you really look at it, let me see. I think I have backup slides that talk about all of them. All right, the constructions. All right, the constructions of the microbeads is extremely simple. We just get any kind of polystyrene bits, and we synthesize our iron oxide nanoparticles. And the iron oxide particles you can synthesize by different ways, as long as they have a magnetic, they have a strong magnetic properties, right? Here we're using super paramagnetic nanoparticles, and we just surface functionalize it with the poly-PDDA polyelectrolyte, and then we decorate these polystyrene bits with the particles. Then by doing that, we could roughly estimate what is the magnetic volume of one bit. And the later one is within the particles is already coated with PDDA. Then we just mix them with the microalgae. Then eventually the particles will beautifully, they'll just naturally go and attach onto the surfaces of microalgae cell. Right. So the whole entire process is quite straightforward. Of course, if you want to get into posterior, different part and things like that, then you need a lot of optimization. That's completely different story.
All right. Thank you, Professor Kim. I think that is all for the Q&A session. Thank you so much for your time and for the wonderful talk. I request for any closing remarks that you may have for the audience.
Sure. Thank you. I guess as someone who have been working on research for many years and also have a privilege with working with a lot of really good and motivated PhD students, I guess, especially if you are young students, you are currently working on a PhD or you are about to start your career in research, I just want to tell you all that I want to reinforce your decision. You have made a fantastic choice, because people like us, not only we have people paying us to play our hobby, and at the same time, we also been funded all kinds of fancy facilities to do our hobby. So I guarantee you it's a very successful and rewarding career, and I hope you will be able to make a lot of great discovery in along the journey. Thank you so much.
Thank you, Professor Kim. I request my colleague Kunal to please take over.
Thank you, Professor Lim. Thank you, Mihir, for that wonderful Q&A session. As we can see, a lot of reactions coming from audience. Everyone has enjoyed, and we had a great number of audience sticking back. So thank you so much for that. So this brings us to the end of today's session. We hope that you have enjoyed this broadcast. We invite you to view the edited recordings from the past events in the ACS Science Talks library. At the end of the session, you will receive a brief survey. Kindly share your feedback with us so that we can continue to improve and serve you better. On behalf of all of us at ACS, thank you for joining us today. We hope to see you again soon for more ACS events. Until then, stay safe and healthy.